first of all, soft RoCE, again, is not a new concept. It was developed by System Fabric Works and presented here a couple of years back. And it kind of stood still for maybe a couple of years. And now we want to basically pick up this project and basically complete its submission and make this thing production worthy. So this presentation is about a little bit to remind you what is actually soft RoCE, what we think, what needs to make this upstream, and why we think that actually this is a very exciting project to work on, because we think that it could provide really good solution, really good software-only performance for systems that don't have RDMA hardware, like a student's laptop or asymmetric configurations. So, first of all, soft RoCE is a RoCE device. Okay, it's basically emulates a RoCE RDMA device in software, and as such, it enjoys the same advantages of the RDMA transport and the same underlying assumptions, which makes it extremely efficient as a software protocol. So it's transaction-oriented, it decouples congestion control from reliability. So if you lose a packet once every 10th of the line, 15th, you don't need to reduce your rate. And you can write directly to pinned application buffers that you register memory to. So these characteristics probably make soft RoCE a very, if we implement it properly, it's going to be very efficient. It's going to be a lot more efficient than TCP. Now, this device can be bound to any standard NIC. The only requirement is losslessness. So you can do that either with global POS or PFC if you have, converged network flows. ETS is also recommended if you want to do quality of service between RoCE and standard IP traffic, but it's not a must. And as I said, it's good for pervasive RDMA, and it's good for cases where you want to have, maybe you have some of your computers don't need the highest hardware performance, so you can use that. And by the way, it could also be a good solution for transparent migration using MPRDMA. You can bind InfiniBand and then some paravert NIC using soft RoCE, and then you get that. So let's talk a little bit about the where this code began. I think it's Bob Pearson's, right? Has written this bunch of codes. It's like all the InfiniBand drivers. It's complete. It supports all the objects, all the transports, both user space and kernel drivers. And it's based on very good design principles. For example, the transport itself is implemented in the kernel. The work queues themselves are allocated in the kernel and mapped to user space instead of copied each time. Memory regions are pinned, which means that we can transfer data to memory regions in non-sleepable contexts. Like at the high level, in terms of of the modules, it looks like this. So we have librxc in user space, and we have two kernel modules, IBRXC and RxCnet in the kernel. And just remember that those two, because we want to coalesce them into one. But this is the initial design. In terms of data path, quite a complicated feature. The main takeaways from this slide are, first of all, the purple are the work queue resources, or the CA resources, so they're allocated kernel and mapped to user space. And the thing I want to concentrate here are the execution contexts. So everything green is an execution context. So we have the application that invokes system calls. We have the soft RRQs for TX and RX. So RX is usually nappy these days. And then we have 4 tasklets, or actually quite a bit more. We have one arbiter tasklet that is at the device level, which basically processes QPs that have ready to send SKBs on them. And for each QP, we have 3 tasklets, a response, a send, and a completion. And more or less, those are their roles. So the send tasklet, when it wakes up, its purpose is to translate Wookiees into packets. And the response tasklet is to handle incoming requests. So if there are RDMA writes, they get scattered to memory. If there are RDMA reads, they get put into the responder resources and then processed, again, by the same tasklet to send outgoing RDMA read responses. And if they are just incoming sends, then they grab a Wookiee from the receive or workie or the Shrek and then scatter to memory. So that's the response tasklet. And then we have the completion tasklet, which handles completions to requests that were sent by this RxC device. So those could either be just, send completions and then they just trigger a completion queue entry, or they could be RDMA read responses, in which case they are scattered to memory. So this is the current architecture. Again, good design in terms of that the protocol runs in the kernel, in memory, mapped queues. Just remember those execution contexts. We'll go back to that later on. So in order to basically take RxC to the next level, we have established a new community project in GitHub, and that's the URL. We're focusing on just the plain vanilla kernel and user space library. It's not an OFID package like was the original code. And this is a multi-company effort. Currently, we have contributors from SFW, Mellanox, and IBM. And of course, anybody else that wants to join. And the goals of this project is, first and foremost, just get Softrocky ready for prime time, meaning we want to make it undergo proper testing, both against other software Softrockies and also versus hardware in multiple scenarios, make it robust and production worthy. Second, complete the upstream submission. And finally, we want to continue development. There are a lot of exciting new stuff to do in this driver, and I think it has a lot of potential. So when we look at what needs to be done, we kind of divided it into 2 rounds. The first round of task is what we want to do to get this upstream. And then the second round is what other nice features will contribute a lot to this code base. So on the urgent tasks, we have a few issues to address by the previous two submission rounds to the Linux kernel. Mainly simplifying device management. So as I mentioned earlier, we want to merge these RxC and RxCnet modules into a single module RxC driver. Code cleanups, a little bit CRC code, remove all these module parameters. This code has been experimented with quite a few ways to establish different tasks, and those different code paths are compilation dependent in the code. So we want to remove all those and remain with the most promising ones. And there were also some heuristics that involved lossless networking issues, which we want to address from the root and remove a little bit intrusive code that looked into the queuing disciplines that were rejected by the community. So after this, I'm not talking more about these. This is just like a large, like tens of small changes that are not worth talking about. We're pretty much done cleaning the code. What I do want to talk about are the ones that I marked in red. So the first is, how do we address lossless networking properly? And the second is, how do we enhance this code to support the RoCE version 2, which is routable. And we want to build upon the recent Mellanox Emulex core generic RoCE addressing patches. And in the enhancement sections, I'll talk about how we minimize the execution context that I've talked about, those green blocks before. Talk a little bit about optimized buffering. And I'll briefly say right now that there is also the issue of we can optimize system calls. Part of the fact that we have the work use mapped is that applications, when they want to write Wookiees, they don't need system calls. They can just write it to their mapped memory. And currently, the code uses a system call as a doorbell. I go here, right? And that's that green arrow, right? You fill out a Wookiee in your send queue, and then you use that system call to initiate that send tasklet to start work. Now, in the common case, when you are hardware bound, the application is always going to have its work queue full. And that's very easy to detect. So in that case, I know that the kernel is already busy scheduling packets out. There's no need to do a system call. So I can detect that, and I can add additional packets from user space without any system call. So in all the cases where I'm hardware bound, I can eliminate system calls completely. So this is the item of doorbell system call avoidance. And finally, there are arbitration improvements, which are also a little bit related to execution, so I'll talk about that in a moment. So I'm just going to cover these red issues one by one. Sorry. So the first thing is lossless networking. Now, as a software driver, we want to leverage the benefits of lossless network. I mean, we already have the network pushing back when there's congestion, and we don't want to lose packets in the host because then we lose all this gain, right? So if we have like a transient congestion issue, we want to avoid losing the packet retransmitting, and we want that back pressure to go all the way up to the work queue that initiates the requests. And it turns out that the Linux stack is not really well prepared for lossless behavior, but it's not far from there. We could easily extend that. And we also have pretty good examples. Probably the best example is Intel's FCOE driver, which basically has exactly the same assumptions, right? FCOE requires a lossless network. And the way we want to modify the code is to start with the FCOE approach, where you try to push packets on the send side, and if your queuing discipline is full and is losing the packet, you get an indication, and then you back off, and then you try again when the timer expires. Now, it's a good solution. It's better to the current code, which does a busy wait spin and then kills the core, because if you're having back pressure, you're going to lose packets all the time. It's going to happen every time when software is faster than hardware. You're going to kill the core. That's what's happened in the current code. And by using a back-off timer, we don't kill the CPU. I mean, whenever the queue is full, we sleep, and then we wake up soon enough, but not late enough, so the queue discipline is empty, and then we continue transmission. And as a future enhancement, we want to replace that with a much more efficient mechanism of basically, if it's based on SKB lifetimes. So instead of doing timers and backoffs, I can get a perfect indication when a queuing discipline has made progress by just inspecting when those SKBs have been freed up by the underlying Ethernet driver. So I can do it in an amortized way, but in any case, I can register a callback, and when someone calls free SKB, I get that callback called, and then I can, continue my reposting in that context. So that's what we intend to do after the initial submission. Regarding the receive path, so first of all, it's typically not a problem if software is fast enough, in which case, I mean, usually this is a kernel driver. If it's implemented efficiently, there's no reason why it shouldn't handle easily a 10 gig or 40 gig link. Maybe 100 gig is more challenging, but at least up to 40 gig, there shouldn't be any problem. Of course, this also depends on PCI back pressure, and but if I think that there's a pitfall, it's software, but usually it's not a problem. And the reason it's not compared to the send side, because on sends you do have congestion scenarios where multiple senders target the same receiver, so the senders need to be pushed back. But on the receiver side, I mean, you're sitting behind a single link that's, I don't know, 10 gig, and now you have PCI Gen 3, which is a lot higher. I mean, there's zero chance you're going to lose packets. The only chance you might lose packets is because of software. And again, since we're talking about a very efficient protocol, I don't see that happening, unless I know some bug or somebody, I don't know, nappy switched context to a kernel thread and then got rescheduled or something like that. But even in that case, there's a very easy way to overcome that. And that is basically whenever your receive queues are empty, instead of dropping packets, you pause the wire. And if you want to avoid this having, let's say, getting all your cluster down due to a software bug, you can do that a little bit more fancy by saying, let's not pause the wire indefinitely, but pause the wire for the next 10 microseconds. Now, 10 microseconds is more than enough for any driver to post a single additional receive wookie. So what you get is that effectively, you back pressure the wire at the rate that software consumes packets, while if the host dies, after 10 microseconds, all the network frees up. So it's a good trade-off. It's very easy to do. We'll propose a NetDev feature and add that. I think there are a couple of NICs that already have this option to turn off and on back pressure when the receive queues are empty. And we want to introduce this notion of a timer, which seems more robust. Now, there is this issue of virtual lossless networking, which is a very big issue. And the thing is that none of Linux virtual networking is ready for lossless networking. Not VirtIO, not the bridges, not OVS. And the way to see that is think about two virtual machines that talk over VirtIO in loopback and try to think what happens. It'll happen all the time. This virtual machine, the sender side, is a tiny bit faster than this virtual machine. And it pushes packets down. And what's going to happen to them? Anyone has an idea? What's going to happen to those packets? Okay, I'll challenge you.
Either go on the same thing?
No, not on the send side.
On the receive side, it runs out of SP bus. So what's the put it?
Yeah, but where? Which portion of the kernel drops it? Let's take a Linux bridge, for example. Okay, Linux bridge doesn't have any buffering, doesn't have PFC. It's all a series of synchronous function calls. So when you do, you have this bridge input function. It calls either flood, or if it knows the DMAC, it calls the DMAC on the right port. And if you have that associated with some VirtIO, or you have this dummy queuing discipline, you just send it, and the current bridge code ignores the response. So the packet could have been silently dropped either by a queuing discipline, if it's a physical NIC, or because some VirtIO send queue or receive queue, sorry, is empty. But there's no feedback whatsoever. And if there was feedback, there is nothing to do with that feedback because Linux Bridge doesn't have any queuing. And the same goes for OVS. OVS is like a fancy bridge only at the flow level. And it also has no notion of queuing, just a bunch of flow rules. You push a packet, you look up the rule, and you push it to the right port, and that's it. No queuing. So this is a big hole, and which means that SoftRocky currently will not work with virtual machines or paravirtual virtual machines. You have to use SRIOV, or you have to use or a physical NIC that has PFC properly supported to use SoftRocky right now.
Step queue transmit now return
What?
value or didn't use
Is what?
Does dev queue transmit return a value?
Yeah, it does.
No, when we wrote this, it returned nothing.
Yeah, there have been a lot of advancements, also in tunneling, I'll mention in a moment. Yeah, it returns a value. You know when the packet is going to be dropped, you clone the SKB first. If it's dropped, then you requeue it, and if it's not dropped, then you release a reference. I mean, there are two ways of attacking this problem in the future. I mean, one is to add queuing to Linux Bridge and OVS, which I don't know how easy that's going to be. It's a pretty shocking change of concept. The other is maybe doing some paravert RDMA, probably along similar lines to what VMware has done. Basically a VirtIO RDMA device. So in that case, I can have multiple VirtIO RDMA devices, and I'll loop back inside my VirtIO framework without any queuing, and I'll make sure that nothing is dropped. So I'm going to skip the bridges altogether. Maybe also Mac VLAN. I need to think about it. So in any case, I'm just marking this as an area that's going to be hard, and for that reason, at least for the short term, SoftRoCE requires physical devices. The second issue that I want to deep dive into is supporting RoCE version 2, which is UDP based on UDP. So when we considered this, we had two approaches. One of which was, hey, we're doing UDP. Guess what? We have a UDP IP stack. Let's use it. Let's open the sockets and UDP packets. The second approach is, we're sending UDP packets, but we're not a socket. We're using UDP as a tunnel. So I don't want to open a socket. I don't want to put SKBs on the socket. I don't want to get woke up when there's a new SKB and then pull the packets. I want to be much more efficient than that. And I want to basically be able to tunnel packets using UDP, but I don't want to do that through sockets. And it turns out that the UDP tunneling approach already has broad support in Linux, and one of the drivers that uses those extensively is the VXLAN driver, which does not open a UDP socket, at least not a standard one. It opens a tunnel socket, which tunnels packets. So when we try to compare these two approaches, I mean, there are pros and cons for both approaches. I'd say that the basic or the major advantage of looking at RoCE as a UDP application is that it's you take advantage of the kernel routing. I mean, you can just send packets to any interface. Interfaces come and go. Routing changes. It's not really a device. It's a protocol. I mean, you would have achieved the same if you would have implemented it over from user space over some UDP socket. But this is not a device anymore, and SoftRoCE that's implemented that way is not going to look like a hardware device. It's going to be managed differently. It's going to be configured by different codes, and there are going to be all sorts of quirks and differences between these two devices, which is not what we want. And most importantly, we're going to suffer from performance. As a device, I have much more control of controlling back pressure. So for these reasons, we're targeting the UDP tunneling approach, and as I said, we're not inventing here anything new. VXLAN does exactly the same, and we're using the same functions. So the tunneling architecture looks like this. Basically, you have functions for tunneling UDP IP packets. On the transmit side, you call this UDP tunnel transmit function, and you provide the netdev that you want to go out on. And you provide all the attributes of the UDP header and the IP header, and this function takes care of everything else. So you control the headers of the packet that you want to send out. On the receive side, you open a special kind of socket that's called a tunnel socket, and then you can either bind it to a specific interface or bind it to IP address any, and then you're going to receive any tunneled UDP packet with the designated port. And then you can multiplex one step higher between the RxC instances, depending on the source network interface from which this packet was received from. And I mean, just for the details, the kernel function look like this. It's UDP tunnel transmit or tunnel 6 for IPv6. And then you can create a tunnel socket by UDP tunnel, set up UDP tunnel sock or release. Now, the nice thing about these functions, especially in the receive side, is there's no context switching. It's synchronous calls, basically handler up calls, just what we need. So you registered this socket and up call, and the moment that NAPI pushes up a packet, you get your handler called, and you can continue processing from the NAPI context. On the send side, the QDisk, I think, currently doesn't report the status. It does for dev qtransmit. It doesn't for the tunnel function, but it's a really minor change. We're going to fix that. The final deep dive is reducing execution contexts. And I return here to the existing architecture, which, as I said, is an excellent starting point. But our observation is that all these green boxes inside RxC are completely redundant. And the reason for that is that on the send side, I mean, you get a system call. What do you need more? I mean, you have a process context to generate your packets. No need for a tasklet there. If you're waking up because the queue is full, as I said, you can either use the timer or use the SKB destructor. If you're handling responses, then you get called all the way from NAPI, and there's no need to schedule anything else. First of all, because TCP already does that. TCP fast path processing, if you get an interrupt on the core in which your current executing process runs on and the packet matches that context, TCP is going to copy the payload of the packet, including byte level overhead, within NAPI context right to the process memory. It's going to do that in NAPI. That's called TCP fast path. I mean, if TCP can do that, so can we. So there is no reason whatsoever to have these two contexts, I mean, responder tasklet and completer tasklet, just a waste of overhead and a waste of latency. Finally, we have the arbiter tasklet, and also notice that all these send tasklets are per QP, and at least my intuition was that these tasklets, part of their role was to control arbitration. So if you have 10 QPs, then you have 10 tasklets working, and then these 10 tasklets push packets into those. No, actually that's per QP, but the arbiter tasklet, yeah, it does some kind of arbitration. But the observation here is that for arbitration, you don't need execution context. I mean, take a look at how the Linux queuing discipline layer works, right? It has a really fancy arbitration, right? I mean, it can do any kind of packet coloring, packet pacing, packet, prioritization at any number of levels. It has no context whatsoever. It has only two functions, enqueue and dequeue, and the rest is policies of how you enqueue a packet and how you dequeue a packet. We can do exactly the same thing here. So what are the arbitrations that we need to worry about? Fairness among QPs, fairness among service levels, and within a QP, fairness between the initiator side and the responder side. I think that's more or less it. But I don't need any execution context to do that. I mean, the first time I need to do any progress, for example, take into account the send side. When I get called from, let's say, from an SKB destructor, I'm just going to see, okay, who's the QP that didn't send anything last? Let's take it. This QP last time, did it send initiator or responder traffic? Oh, it was responder. Let's send an initiator packet. And then we're going to extract the next packet from the corresponding wookie and send it, and then we're going to repeat this process. I mean, there's no reason to achieve arbitration by scheduling. So we want to remove, just a moment. Let's, I'll answer questions in 2 more minutes. So let's remove all the execution context from the RoCE drivers. All the per QP tasklets gone, the per device arbiter gone. The progress will be done either from the doorbell system call or by NAPI, or whenever the QDisk indicates that it can accept more packets, which is either the SKB destructor or by adding a new infrastructure to Linux, for example, where you can register handlers on a QDisk that say, call me when you're free to get more packets. I've talked about arbitration already, so we can skip that. Let's finalize the discussion on buffering. So one of the things that the current code does, it takes advantage of the fact that the memory is pinned, but it doesn't leverage that fact for memory copies. So currently, the send side, the code copies all send data into SKBs before sending them out, even though the memory is pinned. There's no reason to do that. I can reference that pin memory, and I know that memory is valid until I get a completion. I just need to change the semantics of the completion to be, I want to generate completion not when I queue a packet to the QDisk, because the hardware is not done with that yet, but when I get the call to the SKB destructor. When the SKB destructor is called, I know this SKB has been sent. That's it. So I can eliminate all copies on the transmit path. Now, I'm a little bit faking something. I still have per byte overhead, and that is the CRC calculation. But going over a single buffer in terms of cache lines is much better than going over 2 buffers. So I'll have much faster CRC calculations by just going over 1 buffer of data instead of 2 and still doing 0 copy. And regarding the receive side, I have to have here 1 copy, right? Because I'm receiving anonymous packets from the network and I need to classify them. I need to process the transport, decide to drop them. So we can't run away from that. But we can still do all this packet validation and processing in the NAPI context without any kind of either additional context or additional requeuing. Again, I'm looking over to this initial code here. Not only do I spawn these response and completion tasks, but I also classify the packets as either a request or a response, and I put it on a different list to be processed later. Why? I can process these packets just as they come, as fast as they come. And again, we're not inventing here anything. This is exactly how TCP fastpath works. They are smart guys. So, especially for Aku, which is much more lightweight than TCP. So this will come for free. And we'll have very efficient receive side processing. So, in terms of status, we have now the code basically ready for submission. It passes all the Mellanox regression tests. We started initial congestion tests and complex setups and pressuring, and the result looks promising. When we have all the lossless switches configured properly, there's 0 loss, and it works just like hardware. And we're looking at submission price. I mean, it's a matter of weeks now for the initial round. And as I said, we have a lot of exciting stuff coming up to make this a really, really good production-worthy driver. So in summary, soft RoCE is a very important building block in the RDMA ecosystem. I think it's going to contribute a lot for the pervasiveness of RDMA. It's going to be extremely efficient. I mean, it's not going to compete with hardware because you still have per packet overheads, and you still do software processing, and you still have to schedule some deferred tasks to gain progress. But it's going to be much better than TCP in all thinkable parameters, much, much better. And we have a new community project started, and I'll finish with a call for action. Come and join us. When we complete the initial submission, I mean, this GitHub is open for everybody. If people want to contribute, I mean, you're more than welcome. All right, questions? Yes, please.
Have you tested it also with the Mellanox RoCE hardware?
Not yet.
Plan on doing so?
Yeah.
You said you're just about ready to upstream the kernel driver. Do you have which kernel version do you think it might handle?
I don't know. I mean, I need to check with the dev guys to see if they're on track, but they told me that they're like weeks before, so I don't know. Yeah.
So stating like we should avoid the memory filling, I think you want to have more memory and really think that when we start the transmission and have still have the context.
Mm-hmm.
You're not reading out. That's what I'm saying from the bottom half of my
Yeah, I mean, there could be a lot of optimizations here. One of the directions to go is just add ODP support for soft RoCE. So, I mean, there are cases where you actually want to have pin memory. I mean, a lot of good places. The cases where you want to have consistent, low jitter, high performance applications, that's where you want pin memory. And the cases where you allow yourself, you know that you're not going to thrash memory, and you allow, you have a long running application, you're going to page in your working set, that's the place where you use ODP. So we can add ODP support for soft RoCE. It's going to be pretty straightforward.
Is there a plan for a mailing list of what we're trying to go along?
I think GitHub has a pretty good job of tracking issues and posting comments. I don't think that we need a mailing list for this. But we do plan to raise issues, I think, and present this in the Open Fabrics for Herbs working group. We'll go into more details than what I can present here in half an hour, so we can discuss these trade-offs. Yeah.
One of the slides you noticed about we think it's possible to
I'm sorry, I didn't hear you.
on one of the slides you noticed about do you think it's possible to implement zero-copy?
No, it cannot be possible. For zero-copy receives, you have to have hardware that holds the context information. That's called hardware RDMA. Yeah.
We're probably happy to implement the exploit the IOAT for zero-copy. Still not probably 0.5 something.
What?
The IOAT, the exactly better for the the TCP stack is using for software, for EX, I class path, the copy of packet, what's the over, and issues on the DNA command, and I will do the copy.
Yeah, IoT. Yeah, right. Yeah. Yeah, it's not zero. Well, it's zero copy in terms of CPU, but you're still copying from one memory location to another.
So the cache is still not corrupted.
Yeah, that's a good point. We can use IoT undoubtedly, especially for MTU size packets. That's true. Good point. Yeah.
In this release, account release, what was this used for?
What?
What flavors of Linux used for?
None. Upstream. This is upstream development. I mean, after we get it upstream, we'll probably pull it into OFED, Mellanox OFED, and then we'll provide whatever backports the current release supports.